All right. Hope everybody's doing well. Anybody have power outage at their house? A few of us? Yeah. No electricity at my house. But I mean, that's nothing new. I lose power probably about 20 days a year, maybe more. So life goes on. We're going to be talking about underflow gates today, which is closely related to hydraulic jumps. Let's start with the announcements here. I handed back the exams in class last time, and if you didn't pick it up, I have the extra papers up in my office, and we can go pick them up from there after class. Your next homework assignment's due on Friday. Homework 11 is some hydraulic jump questions. And then class next Monday is going to be a recorded video, so we won't have any face-to-face class meeting. Any questions on the announcements? All right. Underflow gates can be relatively simple. It could be something just as easy as a steel plate with a piece of rebar at the top as a handle, and it would slide up and down in a metal frame. So it's not a sophisticated piece of equipment by any stretch of the imagination. And you can see that one pretty common application for gates is to control the flow of water in irrigation canals. This kind of simple rebar handle has an upper limit on when it would be applied, because as you'd expect, not only is the steel itself going to be heavy as it gets increasingly large, but as the water's pressing on the front face of that gate, it's also pressing the gate into the frame. And so then you're having to overcome the friction related to the pressure that's applied to the gate. And so sometimes they'll put hand cranks on the top of gates, or even like electric motors to help lift the gate up within the frame. Gates aren't only just used in irrigation, they're also used to control the flow in water treatment and wastewater treatment. And so you may see, if you go to a water treatment plant, a lot of gates to control water into the clarifiers or into flow equalization basins. And so there are a lot of practical applications where we'd want to know how big the opening should be for a certain flow rate. Or if we know the height of the opening, then what's the likely flow rate that's going to pass through that gate? So it's a matter of both sizing and also understanding the flow rates when one's already in place. One of the innovations that's been developed to reduce the force that's required to lift a really large gate is to make the gate surface itself curved, and then to have the gate, it's called a radial gate, connected. And I think this kind of shows it. It's a curved surface that's connected at a central point that the gate pivots about. And so as the gate is lifted up and down, all you're having to do is overcome the weight of the metal and not any of the frictional effects that is pressing the gate into a frame, as if you had something like this. So these radial gates are used. You can see this is a canal. I think it's in the Netherlands. And it's sometimes also used with reservoirs and dams to control flow through spillways. So at its simplest, we can analyze the flow through gates using the energy equation. And there are energy losses, but what we usually do is we first just consider the situation from the perspective of what does the energy equation say if there was no energy losses. And I'll show you on the next slide how we then do account for energy loss caused by friction as it's flowing under the gate. But at its simplest, when you have a gate in place, it's causing water to pool upstream. And so here Y1 is just referring to the height that the water level is rising to in order to generate enough pressure to force the water through that opening at a high velocity. And so Y sub G here is the variable that's assigned just to say how high the opening is off the bottom of the channel floor. And different books use different variables, and so you can't let that throw you off when you're looking at equations. You know, the FE reference manual may have a different form of the equation than our textbook, or some design manual that you're using. Sometimes the height of the gate opening is referred to with the variable W. I'll show you that in a minute on the equations that we're looking at. But the point is that you open the gate some height, and an interesting phenomenon is that even though the gate is open to a certain height, the water continues accelerating even after it's under the gate. And so as the water continues to pick up some additional velocity, then the water surface depth decreases for a few moments and it reaches stability, and then after this maybe it's going to experience a hydraulic jump, maybe it's going to experience gradually varying flow, but Y2 is the smallest depth after that continued contraction occurs. So if we apply the energy equation, what we can do is we can look at the amount of energy that's at location 1 in the form of the depth and the velocity head, and then here at location 2 we can consider the amount of energy. It's accounted for by the depth and the velocity head, and the two should be equal if you had a fluid that was inviscid, meaning it had no viscosity and therefore didn't experience any friction losses. Of course it does experience friction losses, and one of the ways that we know that it's experiencing a frictional loss is because of this continued contraction. So this simple form of the energy equation isn't an effective way to necessarily calculate the downstream depth, but it's just a first way for us to think about what's going on and how energy is being transferred from pressure into additional velocity, and how when it has that additional velocity the depth is lower. So most gates are rectangular because just it's simplest for the gate itself to be maybe the same width as the channel, or to set in a frame which is itself rectangular. So if gates are rectangular, then we can describe the flow per unit width. Lowercase q, remember, is the volumetric flow rate divided by the width of the channel. So you can estimate the the flow per unit width by the ratio of the depths in this formula. But when it comes to actual practical applications, whether it is a radial gate or a flat-facing rectangular gate, and we're trying to regulate the flow, then the orifice equation will describe what flow rate's going to be going under that gate. So C sub D is a discharge coefficient that takes into account the energy loss that occurs due to turbulence. It's a reflection of both the coefficient of contraction. So C sub C here, you can see, is defined as the depth of the water downstream after contraction occurs to the height of the gate opening. Here it's labeled as W. On the previous slide it was Y sub G. So the coefficient of contraction is just, what percent is the downstream depth after it's experienced that continuing acceleration and the depth is decreasing. What is the ratio of that downstream depth to how much the gate was opened? And a typical coefficient of contraction, it varies from about 59% to 62%, but a typical coefficient of contraction is 0.61. And once you know the coefficient of contraction and you have the upstream and the downstream depths, then from that you can estimate the coefficient of discharge, and C sub D is how you account for energy loss due to friction and turbulence. And so now look at the orifice equation. Square root of 2GY1, so that's very similar to the orifice equation that you learned in fluid mechanics, which said, for example, that if you had a tank of water that had a hole in the side of it and water is going out, that you could find out the velocity of the water by the square root of 2GH. So it was just saying, if you want to know the flow rate, then it would be the area times the velocity from that opening. So here this is saying we've got some rising water depth upstream of an opening. The gate is basically an orifice, and so square root of 2GY1, that's the upstream depth, and then W is the opening of the gate, and B is the width of the gate. So that's the area. Here, this term area. So B is the parameter that's into the page. you can't necessarily see it from this side view, but it's how wide the gate is, B. And oftentimes that would be the same thing as the width of the channel. You have to read the problem statement carefully because sometimes the gate wouldn't be the full width of the channel. If we look back to some of these earlier pictures, so here's an illustration of the gate width is different from the channel width. Sometimes they're one and the same. So B is the parameter from side to side, the opening of the gate that way. So here in the energy equation, then the coefficient of discharge would then reduce the capacity to account for energy loss. So let's apply this orifice equation in the problem that's summarized here. We've got a gate that's 4.3 meters wide, so that's B, and Y1 is the upstream depth, that's 2.7 meters is the Y1, and then the width of the, I almost tricked myself, 4.3 meters is the canal width, but here it says that the gate is 1.5 meters wide. So this is one of those cases where B is going to be less than the width of, B for the gate is less than the width of the channel. And W, the height that the sluice gate is opened, is 45 centimeters. And so 45 centimeters is W, and then the depth continues to contract until it reaches this downstream depth, 27.5 centimeters. And so from knowing Y2 and W, you can calculate C sub C. And then you'll have C sub C, and you'll know the upstream depth and the downstream depth, so you calculate the coefficient of discharge, and then all of that can be plugged into this orifice gate equation to find Q. So let's do that. I'm going to pause, give you a moment to do these calculations. Hopefully you've got scratch paper and your calculator with you today. Okay, so you can see I've got the calculations up on the screen. We're looking for a coefficient of contraction to be 0.611. That's just the ratio of after contraction to the gate height. And then if we put it into the coefficient of discharge equation, then the C sub D should be 0.5822. And then finally, if that goes into the orifice equation for underflow gates, we're using the gate width of 1.5 meters, not the canal width. The height that the gate was opened, 0.45 meters, and then square root of 2g depth of the water, multiplying all that by a coefficient of discharge. And I think what we're going to experience is 2.86 cubic meters per second under that gate. If we opened the gate more, obviously you're going to get a higher flow rate through there. It may also change the coefficient of discharge the more you open the gate. But this is just a way for us to model the expected flow for an underflow gate. Any questions on the calculations or the main idea before we move on? Okay. On Monday, we talked about hydraulic jumps and their location. We talked about the capacity curve of the downstream channel. We talked about the capacity curve of the hydraulic jump, and the idea that if you have the normal depth of the channel equal to the depth after the hydraulic jump, so that meaning here y prime 1, the depth after the jump, then it would jump immediately after the gate, because there wouldn't be any need for the water depth to gradually increase to match a different downstream depth. And so here, what made this kind of the ideal case was the fact that coincidentally, the capacity of the hydraulic jump and the capacity of the channel downstream of the hydraulic jump were equal to each other at every depth. And so the normal depth of the channel was equal to the downstream depth of the hydraulic jump. So Now, if we're thinking about gates, sometimes the question arises is how much can you open the gate without drowning the hydraulic jump? Because if you close the gate more than it is right now, if this is the ideal case, closing the gate more would cause the water level to rise upstream of the gate. It would increase the velocity and decrease the depth prior to the hydraulic jump. So, by closing the gate more, we haven't done anything to change the normal depth. So Y2 would remain the same. But by closing the gate more and reducing Y1, that's going to increase Y prime 1. Because what you'll remember from the momentum depth diagram is that the more extreme the transition, the larger the depth. If you have a really small depth prior to the hydraulic jump, that's going to be a large depth after the hydraulic jump. So if you close the gate more than this ideal case, that's not a problem. It's not going to drown the hydraulic jump. It's just going to push the hydraulic jump further away from the gate because it would cause there to be some gradual increase in depth until you had the depth prior to the hydraulic jump that matched the normal depth downstream. But if you open the gate more than it is right now, that's going to bring the hydraulic jump towards the gate and cause drowning. So the process here to find out what's the maximum gate height that's associated with preventing the hydraulic jump from being drowned, then what we do is we first of all calculate the normal depth downstream for given, the geometry of the channel, its roughness, the slope. So just basically find the normal depth and set it equal to Y2, and we want to find the critical depth just to find out, whether the slope itself is mild or steep, meaning if it's a mild slope, there's going to be a hydraulic jump after the gate because supercritical flow can't continue indefinitely if you've got a subcritical slope. And then to find out how big the opening in the gate could be, then what you'd calculate is you'd say it's Y1, meaning the upstream depth of the normal depth. So we're saying the normal depth is equal to the downstream hydraulic jump depth. So now instead of finding Y2, which is what we've done so far, if you look at the Bellinger momentum equation that we've seen up till now, it's been expressed in terms of finding Y2. Let's see, where have I got the momentum equation? Here it is. So the Bellinger momentum equation till now, we've just been using it with a known Y1 and finding an unknown Y2. When a gate's involved and we're trying to figure out what's the maximum height the gate can be opened prior to drowning the jump, now it's a different equation. So this form of the Bellinger momentum equation is different because we're solving for Y1, not Y2. And so we've also made some changes to the inside of the momentum equation. I think previously it was Y2, Y1 divided by YC. Let's just look back at that other version of the momentum equation so that you don't misuse in the wrong place. This is in terms of Froude number. There it is in terms of depths. So let me copy this onto the slide that we're looking at just so we can compare and contrast these two equations. Okay, so if we were finding the Y2, then this is the form of the momentum equation that we're using. But when we're trying to figure out how much we can open up the gate, then it's this. So it's in terms of Y2 being known and Y1 being the unknown. So the Y sub C, the critical depth, is still an important parameter, but it's in terms of the known downstream depth Y2, both inside that square root and then also where we're dividing by 2. Well, let me erase this here. And so if you close the gate, then it just causes the jump to run away, no problem. You're not drowning the jump if you close it more than that maximum gate opening. But if you open the gate more than the maximum gate opening, then the hydraulic jump moves towards the gate and it becomes drowned, and it's not going to dissipate energy in the same way that it would if it's free flowing. All right. So this is just a review that last time we pretty extensively talked about different hydraulic jump locations. So let's go through the process of some calculations to find out how much we can open up the gate. So whether we call it Y sub G, whether we call it W, we just basically want to know how much can we open this gate without drowning the hydraulic chump. So the steps that we need to follow here is we know the channel's slope. Here the slope is 0.3%. We know what the channel's made of and therefore its roughness. So the N value is 0.02. That's the roughness of the channel, the flow rate that's going through it. And then it's a 5-meter wide rectangular canal. So we can use that to find out what would be the normal depth. So step 1, calculate the normal depth using Manning's equation. And so after we do that, we're going to say let that normal depth calculated by Manning's equation be what we're considering y after the jump. Just to eliminate any confusion where we're talking about y2 or y1 or y prime 1. Here I'm just saying let's call that y after the jump, and then here's the formula that will allow us to find y before the jump, and that is going to be the contracted depth. So remember that after the gate, the water continues accelerating because of that coefficient of contraction, because it's got a lot of pressure to the left of the gate, a high velocity. It continues to accelerate briefly. And so y before the jump is the contracted depth. And so we'll have to go through a process of calculating the coefficient of discharge and knowing what's the critical depth in order to find out how much we can open the gate. So let me just write on the whiteboard a summary of the calculations that you'll need to go through. So first thing, normal depth. Find y using Manning's equation. All right. 2, find the critical depth. And we're going to use that critical depth just to make sure that the normal depth is greater than the critical depth, because that's one of the ways that we can diagnose whether the flow downstream of the gate is subcritical and whether it's going to go through a hydraulic jump. All right, now 3, for the max gate opening, there's a couple of things we want to do. First of all, find y before using the momentum equation. And then the coefficient of contraction is y before divided by w. And so if we rearrange that, then w is y before divided by coefficient of contraction. And here it says, let's just assume a typical coefficient of contraction of 60%. So then that'll allow us to find out how high the gate opening can be. And then that would be like step 3 here, solve for W. And then 4th is let's find out what would be the upstream depth of the gate. So how high does the water have to rise in order to force the flow under there? And for that last part, we're using the orifice equation. So to find the depth behind the gate, 4 is depth behind gate. Then we're using C sub C of 0.6. Use the W from step 3 and solve for y1. Because we're given Q, we know C sub C, we know y2, so find y1. All right. So, starting with the normal depth. You remember Manning's equation. Here it is. For a rectangular channel like we've got, if this is a rectangular channel, then the width of the canal is 5 meters, and what we don't know is the normal depth. So area is 5 times y, and wetted perimeter is 5 plus 2y. So put that into Manning's equation with the known flow rate, with the end value, with the slope, and find out what's the normal depth that the water's flowing at. Let me just interject with a couple of comments here as you're working. All right, so here in this setup, what we are doing is starting with Manning's equation. And if you put it into the solver, what you should get is that the normal depth is 1.78 meters. And that's going to be, that normal depth is what we're setting equal to the y after the jump. So we're saying that, we want to open up the gate as much as possible, and that as much as possible is associated with the depth after the jump equal to the normal depth. So that's why we've calculated normal depth. And then the critical depth, 1.366 meters. That's useful to us for two reasons. First, it's just to make sure that we have a mild slope and that a hydraulic jump is going to occur. Because if the critical depth was larger than the normal depth, then that means you have supercritical flow and there's not going to be any hydraulic jump. But here what we found is that the critical depth is less than the normal depth. And so that is indicative of subcritical conditions and a mild slope. So it is going to experience a hydraulic jump. And the other reason why that critical depth is useful is if we look at the formula for finding the depth prior to the jump, it is dependent on knowing the critical depth. All right, so that kind of satisfies the unknowns in step 1 and step 2, the normal depth and the critical depth. So now in step 3, what we're going to do is apply this Bellinger momentum equation and find what is y before, and then when you know y before and the coefficient of contraction, solve for w. All right, so I'm going to pause again, give you some additional time to continue the calculations. Okay, so if we know that after the jump, the depth's 1.78, meaning the normal depth, and the critical depth is 1.366 meters, so we put all of that into this momentum equation to find the depth before the jump. And that says it's going to be 1.022 meters. So let's go back to the sketch. 1.022 is this depth before the jump. The gate's open more than that because remember it's contracting by 60%. So normal depth is 1.78, depth before the jump 1.022, and then the height of the gate should be 1.703. So it's kind of interesting that the gate's open almost as much as the downstream depth. The downstream depth after the hydraulic jump is 1.78. So the gate's open 1.7. It continues to contract down to about 1 meter. Then it goes through the jump back up to 1.7 meters. So it's only because of the contraction that the flow becomes supercritical. The gate was open more than the critical depth, but the fluid continues to accelerate after the gate. So that addresses parts 1, 2, and 3. So finding the height, the maximum height of the gate opening. The last thing that we were curious about is how deep is the water upstream of the gate. And so to do that, to consider that, we'll use the orifice equation. And so the information there is, we know the coefficient of contraction is 60%. The flow rate was already described as 25 cubic meters per second. So the unknown here is Y1, and that exists both in the square root of 2gh, square root of 2g y1 component, and also in the coefficient of discharge. So we've got it in multiple places. So this isn't one that I don't think we'd be able to readily solve this algebraically directly in the calculator. You maybe would just want to invoke the solver again, the numerical solver, where we know the left-hand side of the equation is 25 cubic meters per second. We've got the unknown in 3 different locations here. So it'll work out to the water has to pool upstream of the gate 1.88 meters. So that's how high the water pooled upstream of the gate so that it has enough velocity to contract down to the 1.02 meters prior to jumping back up to the normal depth. I love having questions like this on the exam. I just can't get away from it. The final exam, I love to have like underflow gate because there's so much happening all at once. It's just a rich target for good questions because you've got the pooling upstream of an obstacle, you've got the contraction prior to a jump, you've got a hydraulic jump, you've got the tailwater where you're having to calculate the normal depth using Manning's equation. So, you know, this is a really valuable example. I would emphasize it would be time well spent for you to study this prior to the final exam. I haven't written the final exam yet. For some reason, I'm like a moth to the flame on questions like this. I can't get away from it. I love that question. So I wanted to remind you of what is a wide channel. Like there's a technical definition of a wide channel. And a wide channel is one where its width is more than 20 times the depth. And what's significant about it is when you have a channel that wide, the friction related to the side is negligible. So it doesn't really matter so much whether you've got a rectangular channel or a trapezoidal. The wetted perimeter over here on the side is really small in contrast to the bottom width when you've got the width more than 20 times the depth. So that was our previously described technical definition of a wide channel. If you've got a really wide channel, it's kind of interesting that we can calculate the normal depth with some abbreviated approach that relies on the flow per unit width. So this is a simple way to find the normal depth where we don't have to put in the area, we don't have to put in the wetted perimeter. This only applies if it's rectangular, it only applies if it's really wide. It doesn't necessarily have to be rectangular, but if it's wide, we've got that simplified way to calculate the normal depth. And here's just kind of an illustration that the hydraulic radius is about the same as the depth when you get beyond that threshold of 20 times. So if you've got a wide channel, then the gate equation also becomes simplified. So here's the normal gate equation for any kind of, whether it's wide or not wide. But if you have a wide channel, then the flow per unit width, and this here, it's a C sub D, we put in the full version of C sub D, so that includes the coefficient of contraction and the ratio of the depths. So it's just kind of a simplification that arises if the channel is wide. All right, that's all the time we've got. If you didn't pick up your exam previously, if you have any quizzes or exams that haven't been collected, we can go up to my office and get that now.